Okay, so yeah, I'm Francesc Campoy, and I'm a developer advocate for the Google Cloud Platform, but actually I work most of my time with the Go team. So I've been working with the Go team for 2.5 years now, and since then I've been writing pretty much just Go and JavaScript because there's web pages that I have to do, and I'm really happy with it. So I'm going to be talking about Go best practices. So first of all, what is a best practice? So Wikipedia is the source of all truth. So a best practice is a method or technique that has consistently shown results superior to those achieved with other means. So for me, it's basically something that normally works better and better for me in Go is that it produces code that is simple, it's readable, and it's maintainable. Doesn't mean faster. And actually, most of the code that I'm going to show, it's going to be probably slightly slower. But actually, the code base that you're going to end up having is going to be way easier to understand. And depending on what language you're coming from, actually having a 1% slower is not going to make a lot of difference. So these best practices to have a healthy code base, again, if you need something that performs really, really fast, of course, you can always write some part of your code, which is just the code that needs to be really, really fast in a slightly not that beautiful way. But the rest should be readable. OK, so I'm going to start with bad code. So yeah, this is pretty awful code. What we have is a struct. It's a gopher. A gopher has age and years in a name. And I want to implement this function, which is write to. So given a writer, so there's actually an interface in the IO package, if you know it, which is writer to. So given a writer, it returns the number of bytes that it has written, and an error is something went wrong. Okay. So what I have to do is I have to write first the string, and I'm going to be writing it to a binary channel. So I have to write first the string, then the integer, and then return everything. So what I start doing is, OK, I'm going to write binary of the size of the string, because I want to say this is the size of the string, then I'm going to write the actual bytes. So I do that, getting the length of that string. That I want to print it as an int32, because Gopher names are short. And I'm going to print that. I'm going to write that into binary. So I'm saying, OK, write that as a little endian into this writer. And that could fail. That could return an error. If that error is nil, it means that everything went fine. I'm going to continue, and I'm actually going to say, OK, so I wrote 4 bytes, because 32 bits is 4 bytes. And then I'm going to try to write the actual string as a slice of bytes. So I'm going to actually write those bytes into the writer. Again, this could fail. I'm going to add the number of bytes, because that will be, even if it fails, it might have failed after writing some bytes. So I'm going to add those numbers and say, OK, so if it didn't fail, now I'm going to just write the age in 64, because gophers can grow very old. And check if the error is nil. If the error is nil, that worked out. So I can add 4 bytes to the count. And then return, and return. So this is code that is really bad. And what's the first thing that you could change? I mean, there's a lot of things to change, I know, but
the error checking?
Yeah. OK, so in Go, there's something that we do very often, that it's early return. So do what is the shortest thing to do first. So in this case, if the error is not nil, what you could do? You could just return. You don't have anything to do. So we're going to just change that. And all of a sudden, the code looks slightly better. So now what we're saying is we have the same steps all the time, exactly the same steps. It's exactly the same code, just doing early return. So early return is something that we do very, very often. That's why in Go, actually, we don't write the else that often. It's kind of surprising, but else is a keyword that we don't use very, very often in Go. So, and also the fact that there's less nesting, so less tabs. It's not only good because it looks slightly better. It's also good because when you're reading code, you can actually forget about. So you say, OK, if that fail, you're done. You don't have to understand. It's like, oh, if you're inside of that if, it's because that error before was actually nil. It's like you just keep on reading code, and it looks, it's like you're telling a story. So that's the first best practice. Early return, very important. Then, again, one of the things is we're repeating a lot of things here. We're writing into binary, increasing the size, writing to binary, increasing the size, writing to binary, increasing the size. So that's not a very good idea. There's the dry principle, don't repeat yourself, which is not really, really important, but when you can apply it, you should. So we're going to try to do that. So what I do is I create this type, a bin writer. A bin writer is a thing that writes binary stuff. And what I'm going to do is I'm going to have a writer inside. So when you write into the bin writer, actually it's going to write into some other writer. And I have the number of bytes that I've written, and an error is something failed. Now, the write method, what it does is it checks if something before failed. If something before failed, I don't do anything. I'm done. But if it didn't, if so far all the operations called on this writer were successful, what I'm going to do is I'm going to write whatever value I got. So it's an empty interface. Any type is an empty interface because an empty interface is all the types that implement at least no methods. So that's any type. So it's like the equivalent of Java to object. It's the global thing. So we're going to try to print that into binary. And if that doesn't fail, we will increase the size of bytes that we've written. So now, thank you. I cannot close it. OK. Thank you, Apple. Anyway, so now with this type, which is this tiny little utility type that it's not really that useful, but it's just right here. Our code looks like this. And it's doing exactly the same thing. Now, what I'd say is like, oh, I'm going to create my bin writer given this writer, the writer that I got passed from the write to. And I'm going to write first the length of the string, then the string, then the 18 years, and then I'm going to return the size and the errors from the bin writer. And that's it. It's exactly the same code. But now all of a sudden, when I read this code, I know what it does. When I read this code, I hate the developer that wrote it. So this looks like pretty good code. But there's a little problem again, which is imagine that there's a new developer that comes. We add a new field to the Gopher, and it's a string. And he doesn't realize that actually you have to write first the length and then the actual string. He forgets about it, and that's probably a nice bug to find. So what if instead of having this information on your code, we just move it to the bin writer? So what we can do is we can use a switch type on our write method and say, OK, you can pass whatever you pass, whatever you want to pass. If what you're passing, so this is a switch with a type. So basically what I'm saying is switch on the type of V. V is an interface, an empty interface. So I can say, oh, if the type of V is a string, then S is going to be V as a string. This is what we call a type assertion. So if that doesn't work, if V is not of type string, it will panic. We know that it is in this case because inside of a case, so otherwise it couldn't work. And we say, OK, so if it's a string, actually you have to print first the size as a int32, then the actual the bytes. And if it's an integer, I want to print them as int64. Integer int is of a variable size depending on the architecture. So we want to make sure that all our machines have the same format. And otherwise, do what you were doing before. And now our code that it's kind of hidden now, that's just write the name and then write the age. That's it. Now there's something that we try to do with Go, which is the code should be very simple to read and without repetition, without stutter. And there's a thing that we repeat here, which is, oh, if it's a string, get it as a string. If it's an integer, get it as an integer. Is there a way to remove this line and this line? Yes?
There's a special form of the switch where you can assign it to a typed variable.
Exactly. So what you can do is you can say that v.type, you're getting that value and you're declaring as a variable. And this variable will be available in every single branch, in every single case. But in every single case, it will have a different type. Meaning that now x, in this case, is a string. So you can do length of that string. But in here, it's an integer. So you can actually do the int64 of that. And in this case, default, it will be empty interface. So the type of x in here is just empty interface, which works. So now with this, the code is just like it was before here. But now it's just slightly simpler, 2 lines less, but can be useful. Yes?
And int is a superset of int64?
No.
32?
Int is an integer that is the size of the machine's, how do you explain it? So if your machine is 32 bits or 64 bits, you have ints of 32 bits or 64 bits. So when you don't care about the size of your int, you just use int. If you actually care, and if you're writing to binary, you should care, you're going to write either int32 or int64 or int8 or 16 or whatever you want to use. OK, so now what we're going to add on top of this is imagine that we're actually encoding binary into a network, and that we want to either write everything into the network or nothing. We don't want to start writing a gopher and then fail in the middle. So what we're going to do is we're just going to replace the number of bits, the number of bytes that we have written before by a buffer. So this is a bytes.buffer, which qualifies it pretty well. It's a buffer of bytes. So what we're going to do is just simply changing this line here. So before, what we're doing is we write it we write the value into the writer, and we count how many bytes we wrote. Now instead, we're just going to write it to the buffer. That's it. But now the problem is the buffer has to be flushed. If you don't flush the buffer, you're not writing anything into the network. So what we're going to do is modify our code to actually call flush. And it turns out that flush returns 2 values: the number of bytes that were written and an error if something failed. So actually what you have right now is you're saying, OK, when you do flush on this writer, if there was an error before, say you didn't write anything and return that error, which could be something like this gopher is not a good gopher, couldn't encode to binary at all, so I couldn't do it. But if that part worked, then we actually flush that buffer into the network. And now this could fail again, but it could fail because the network is down, for instance. So the different errors. So with this, actually, you end up having code that is really simple, and it's really easy to understand. Compared to what we had before, it's way easier to understand. But as I was saying, now, if you're calling this, and your gopher had 100 fields, and the first method fails, you're actually going to still do the 99 method calls that go after that. So this means that eventually this could be slower, but I think it's worth having code like this, run the code before, and pay the price of having a little bit of overhead. Now we're going to see another piece of code, which is something that we write pretty often, which is web servers. This is pretty much a whole web server, except for missing 2 lines of code that I'm not going to show. But basically, when you write a web server, you have HTTP handlers. And the signature for an HTTP handler is exactly this. It's a function that receives 2 arguments. The first one is a response writer, which is an interface. And you can do multiple things. One of the things is to write. That's why it's called writer. But also you can set headers, and you can set the status code. So you can say 200 or 500 or whatever happened. And you also get a pointer to a request. And the request contains all the information from the incoming request. So, and this is the type that it has to have. So you cannot modify it. So this means that it doesn't return an error. So if you have errors during this function, you actually have to handle them. Meaning that you're going to do something, and if that fails, you're going to handle the error in some way. So in this case, we're just creating an error page with the status internal server error, also known as 500. And we're going to log some error. And then we're going to return. Then we do something else. And if it fails, we do exactly the same thing. So you might end up having this code over and over. One of the solutions could be to write this in a function, but actually there's a better way, which is what we call function adapters. If you come from Python, very often they're called decorators. But it's exactly the same idea. If you think about a decorator in Python, it's actually a function that, given a function, returns a function. But when you read it in Python, it's really hard to understand because actually you don't have any type. So it's kind of magic. In Go, a decorator is this function that receives a function and returns HandlerFunc. Actually, HandlerFunc is also a function. HandlerFunc is the function that matches exactly this signature here. This is actually also known as HandlerFunc. So now our function, what it's going to do is it receives a function that it does exactly the same thing, but this one here returns an error. Okay, so the incoming function returns an error. The one that we return, it doesn't. So what we do is we just call that function, and we handle the error. That's it. Now our handler here, it can actually return the error. So this function here, do this. If it fails, just return an error. Do something else. If it fails, just returns an error. So in here we like, oh, doing this, that failed. That's all the information that you have to add. You don't have to say log it to the so log an error, or create a whale, flying whale, whatever you want to create. You don't need to do that. That's going to be managed by only this function here. And so what we're doing is this function, given a function, returns another function, HandlerFunc. A HandlerFunc is actually the same thing as this type here. We do this very often to add middleware. So you could imagine things like, again, if you're creating the web page and you fail while you're creating it, if you have already sent any bytes to the response, it's too late because you cannot send headers. So if you say 200 and then you start sending your output, and there's like, no, 500, sorry, that's too late. You cannot do that. So very often what we do is you will actually have a buffer. So you will pass to this function, will pass a buffer. And only when the error is nil, you will actually flush that buffer. Otherwise, you will generate an error page. So you will see that pretty often. OK, and now a little bit less about code, and now how to organize code in general. I've seen a lot of code, and one of the common things is you start always by license. If you are in open source and you're not writing licenses, you're not doing it correctly, because you're not writing open source then. I've seen it very often, especially with code that I like and I want to reuse, and I cannot. So write licenses. Also, we have build tags. Build tags in Go are actually a pretty cool tool that allow you to compile a file depending on some tags. So the tags could be the version of the compiler. So you could say, actually, this works on 1.3. So on 1.3, we added some really cool thing that you want to use. You can write that code and say, and if it's less than 1.3, have this older version that is not as fast or whatever. So you can have different code. We use it also very often to say, oh, if you're building this for App Engine, use this file that it's going to use the correct thing for App Engine. But if you're running it locally, build this other one that actually defines the main package. So you can have these things pretty easily. Then you have package documentation, which is very important. And then you have the import statements. The import statements, we sort them alphabetically, which you don't need to care because there's GoFunt that will do that for you. So GoFunt is this really cool tool that you can call it pretty printer, but it does more and more. So now we don't use the new GoFunt is Go imports. Nobody uses GoFunt anymore. And Go imports, in addition to that, it will actually write the whole import statements for you. So the way we do it normally is we start with the standard library. So all the packages from the standard library at first, then blank line, then all the packages that are imported from third-party libraries, and then blank line, and all the packages that are imported from your own code. So I'm just going to do this little demo. I'm going to create main.go. OK, so I'm going to just write function main. Hello. This is not correct Go code.
It says format. But
There's, I'm going to make it even worse. OK, like this. This is, actually, there you go. Beautiful Go code. OK, so this is really bad Go code. But it's not matching the format. But in addition to that, it doesn't even compile for two reasons. One, every single Go file starts with package. I'm not saying package main here, so that doesn't work. And also, funct is not declared, because funct is a package that I'm not importing. So I'm just going to save, and that's it. It will do it for me. So, and you can do cool things like, if you've used Gorilla before, I can use Gorilla the router, and it will, I don't know, a route? There you go. So it's able to find all the packages inside of my Go path, and find the packages with the name that matches this, with an identifier inside that matches the second part. So anyway, so that's the import path. And then the rest of the code is pretty much whatever you want to do. But actually, I've seen a lot of people that start. So I guess that if you're coming from C++, you could actually imagine that if you have to declare in order, so you have to do pre-declarations and all these things. Go doesn't need that. So in Go, actually, the best way to write your code is the first piece of code should be the most important one, whatever that is. And normally all the utility functions and all the code that is just there to help the rest of your code, that's going to be at the end. So when I start reading a file, I'm going to read first documentation. Oh, this package does this, and it uses all these things, and this is what it does. Rather than actually having something like helper utility that does something weird that I don't know when it's called. So this actually, this is a convention, but I think that this is the best way to write your code, except for the license. License is not a convention. Okay, so documentation is very important. You should always document your code. So the first part of documentation that we have is the package documentation, which is just. So I heard someone during OSCON saying that Go doc is like Java doc, and it's not. Go doc is text. That's it. We don't have any special symbol to represent parameters or return values, or no, it's just English or whatever language you want to use. But basically what you say is all the documentation for the package is going to be right before package without blank lines. If you put a blank line, actually we'll ignore it. So no blank line between the end of the comments and the package line. And then just code. Text. It's also very important. So in Go, when you have any identifier, it might be variables, types, functions, if the identifier for that thing starts with a capital letter, it's exported, meaning that it will appear as part of your API, meaning that you should document that. If it's not documented, you will have documentation that only has code and no text. If it's not exported, it's also good to document it, but it's not as important. So for instance, in this case, in this case, we have this type author, and if you check, actually I think that this changed it. Yeah, it is changed. But anyway, not important. We're going to get something else. So out of the code, you're going to get this pretty beautiful documentation. So these are generated from the code directly. And you can go around. You have all of this is just code. And at some point, you get to the index. You can get all the constants, all the variables. You can see. And when you get to functions, you can actually even click on the name, and you will see the actual code defining that. So this is pretty useful. This is godoc.org, by the way, and it's really, really useful. It allows you to find any kind of code, so you can search for anything. So if you're interested in doing MP3, you will find MP3 encoders and decoders and these kind of things. So really useful, Godoc. Now, especially for people coming from Java, names in Go are short, to the point that when we have local variables, very often there will be just one letter long. So it's very usually you're going to see a variable called I, which is for an index, and it totally makes sense. And calling it index is not going to help in any way. So I is just good enough, and that's what we use normally. Is if it's one letter is enough, sure, go for it. When you're actually exporting something and it's going to be used from outside, then of course you're going to have to be slightly longer. So But it doesn't mean the longest name, it's not more useful. It has to be as long as it needs, but as it has to be readable, understandable, and self-explanatory. Meaning that, for instance, in the JSON package, we have Marshall indent. We could have written Marshall with indentation, which is better in English, but it doesn't really add anything, and you have to write it at some point. Some people say, oh, well, you don't really need to write it because your editor is going to do it for you. OK, you have to read it. We spend more time reading code than writing it. So actually, the length of an identifier, you're going to read it a lot of times. So if you have a typo or something like that, the shorter it is, the easier to find. Also, it's important to say that when you have a package in Go, to use any identifier from that package, you have to write the package name again. So the JSON encoder, it's just encoder, because it's part of the JSON package. So to use it outside of the JSON package, you have to write JSON.encoder. So calling it JSON.JSON encoder doesn't help. So it's important, like bytes.buffer. It's just bytes.buffer. It's not bytes buffer bytes. Then also in Go, you can have as many files as you want per directory. So you can have only one package per directory. Okay, so in a single package, in a single directory, all the files that you might have belong to the same package. But you could have only one. You can have multiple. Why could you have multiple ones? First reason is to avoid having 10,000 lines files. It's a pretty bad idea, especially if you're going to have to merge them. It's going to be fun. Also, it's important to separate code and test. Actually, in Go, we have a testing library. It's part of the testing package. That's part of the standard library. And it allows you to do tests, and it actually separates what is test and what it's not by this convention of writing _test.go. Anything that is _test.go is ignored when you do go run or go install or go build. It's only taken into account when you do go test. So it allows you to separate your code very well. And finally, it's to separate the package documentation, meaning that imagine that you have 5 files. Where do you put the package documentation? Maybe there's a very good place to put it, but most of the time there's not. So what we do is we create a new file called doc.go that just contains one line at the end that says package and the name of the package, and all the rest is just documentation. So you will see that very often. So if you check the standard library, you can find it in net-http. I think, yeah, net-http is 47 files. Which one is the one that should have the documentation? Doc.go. It's just easier. Finally, your code should always be Go gettable. And if it's not, yeah, I know. If it's not, you could still have a very successful project. But but anyway, it's better to do it. So GoGet is this tool that will allow you to download all the code directly from any public repository. It will compile it, and it will install the binaries, the corresponding binaries, into your Go path/bin. So all of this, it's built in a way that actually, if you follow the conventions, working with Go code, it's just very, very simple. What we do normally is you separate your code into two kinds of codes. One is reusable code. The other one is code that you're not going to reuse. It's impossible to reuse. What kind of code is impossible to reuse? Main package. Main package, you cannot import it, so you cannot reuse it. So very often what you're going to see is this actually from Candy Store, which is a project that Brad Fitzpatrick wrote. And I think it's a very good example of what Go code should look like. And you have two different directories. One is common that contains different commands, so camget, cammount. And inside of each one of these, there's a main.go. When you build that code, the main.go file will be compiled to a binary named camget, cammount, or camput, or whatever. So this is actually very easy. You just install everything, and these binaries will appear in the Go path binary. And then the part that you can reuse. And the part that you can reuse, you can start with package. That's a very good way to do it. You can rename it whatever you want, but package is a very good way to do. And you're going to have, for instance, authentication. Maybe the authentication for Candy Store is very useful, and you can use it in a different project. So if you do it this way, people will be able to reuse your code very easily, if you have a license. So it's important to just ask what you need for. So if you are writing code, use interfaces. This example, write to, so it's again the same Gopher as before. You could say, oh, write to file, and you're going to create this write to file method that, given a file, it writes a Gopher to that file. And the code is going to be very simple. It's just going to call write. That's it, and close probably. Now the problem is that, what if I want to use it and I want to write it to a network? Now I have to change my API. So actually, it's like, oh, actually no, read writer. Read writer is an interface on which you can do read and write. But actually, you don't even need the read part. So just do io.write, which means that now, just probably the code inside didn't change at all. And now what it means is that write to writer, or also known as write, it will allow you to write that Gopher into a file, into a connection, into a zip encoder, or whatever you want to use. So it's really important to have the smallest interface that you can as your input. Also, this is something that took me a long time to understand when I started working with Go, which is the fact that having implicit satisfaction of interfaces, meaning that when you satisfy when you implement an interface, you don't need to say it. You don't need to write implements something. In Go, you don't need to do that. And it actually allows you to write really good code which is completely independent one of the other, and it still works. So this example, it's a real example, but with really bad code that I wrote. And what it does, it's actually a web app on which you write a mathematical function, so x squared, whatever you want to write. And there's two parts. One part will parse that into something that you can execute, and the second part will render as an image. So you will get an image with that function, whatever it is. So what I wrote was this code, pretty much. So it returns, so I call parse with a given text, and that returns a function. And then I call draw with that function, and that returns an image. And then I encode that image, and then done. Pretty easy. So this is actually the whole code. Now, the important part is parse and draw. Those are the big things. So I started writing this code. Okay, so the complicated part is not here. But basically, there's this parseFunc method type that has the text that I parsed, and then the resulting function, which is a val. And it has, parse returns a parseFunc. And it has the method eval, which is the only important one, because when I call eval, I'm going to evaluate that function. So if I have x squared, if I pass 0, I get 0. If I get 1, 1, 2, 4, so on. So this is actually pretty simple. Now I wrote draw. And what I did is like, oh, so my draw, what it does is, given a parseFunc, it just creates the image. Okay, pretty simple. But now, all of a sudden, draw parseFunc, it gets a parseFunc, and it depends on parser. So my parsing depends on my, my drawing depends on my parsing. Do I need that? No, actually, I could say, oh, actually, I just need a function, and that function has a method eval, and that's an interface. Anything that has an eval method that, given a float, returns a float, works for me. The rest of the code didn't change. So what I'm saying here is, all of a sudden, my draw package is completely independent of parse. It just needs something that it can evaluate. Which means that now I can test it. So I can pass anything that is a function. So, and that function could be my test_func, which is an actual function. So that function could be, what is this? Here, math.send to calculate to do that operation. Or I could do the identity function, which is just returns the same value. And this allows me to write code that actually I can test really easy and say, oh, if I'm getting the identity, which I'm passing here, I expect this result. I don't need, if I have a bug in parse, draw will keep on working anyway. So this is important to have as little dependencies as you can. And now for concurrency. So one of the most important things of Go is that we have a very useful concurrency, and it's very powerful. which means that people use it, which is good. But sometimes they use it a little bit too much. So one of the things is putting concurrency in front of your API. It's actually a pretty bad idea. So let's see why. I create this function, which is do concurrently, that given a job, which is in this case a string, but it could be a function or whatever you want to do, it calls that function inside of a new Go routine. So actually, it will execute something later on. Okay, it doesn't wait, just says, okay, this will be executed at some point. And to do that, actually, you have to pass a channel of errors, because that channel of errors will be used to send the error. So basically, the do concurrently starts some job and says, once you're done, send the resulting error to this channel. Which means that now I can create a channel of errors and start 3 different jobs and just calling do concurrently. Those 3 jobs will be executed concurrently, so eventually in parallel. And now I can wait for the errors to come back into that channel. So basically, you start all of them and you wait for them to go back. So this is pretty useful code. Now the thing is that, how do you change it to do this sequentially? Actually, what you have to do is you have to create the channel anyway, call a function, wait in the channel, call the function, wait in the channel, call a function, wait in the channel. A little bit of a pain. Now let's do it the other way around. And just have, instead of do concurrently, have do. Now do, what it does is just what it has to do. That's it. And instead of putting the error on a channel, just returns the error. Now, if we want to call the same way as before, so concurrently, what we have to do is we create the channel, and then we call the function. Now, we're calling the function and sending the result of the value, the result of that function, we're sending into the channel. So this is the only difficult part that we have to do. The fact that, oh, this is actually called in concurrency, and we're passing the result to the error, to the channel, and then we wait for them. So it's pretty much, to do it concurrently, this code and this code are actually really similar, just 2 lines extra. But now, if you want to do this sequentially, it's a for loop. That's it. So actually, when you're writing Go, if you expose sequential APIs, using them concurrently, it's very easy. And using it sequentially, it's obvious. So normally, avoid having channels and all these things in your APIs. It makes everybody's life easier. And now the best practice for concurrency, and there's an opportunity of winning a Gopher. So I will ask a question, so pay attention, please. I'm almost done, don't worry. Okay, so one of the things is we use Go routines very often, and very often we have so in this example, I have this server, and what I want to do is I want to start a Go routine that manages the state of this server, okay? So what I do is this server, which is a struct, I create the when you do new server, it creates a server, so it puts a channel inside. We'll see what the channel is for a little bit later on. And it starts the run function in a different Go routine, okay? Now, you can do this very easily. The problem is, how do you stop it? When you're done with the server, what happens? If you don't have any way to communicate with that Go routine, you cannot stop it, which means that you're going to end up having a lot of Go routines running for nothing, and that's actually memory that you're wasting. So what we do is, actually, we use this quit channel. So our run function, it's doing an infinite loop. So while in Go, it's written for, and if you just write for, that's an infinite loop. So this is an infinite loop, and it does select. Select, it tries to do multiple operations on channels at the same time. So what we're trying to do is to read from this channel, which is time.after. So every second, we do something. So that could be we're doing the work that we're supposed to do. The server is actually responding to queries or whatever it's doing. But at the same time, we also have quit. And quit, what it will do, it will just quit. Don't pay too much attention to this code yet. Basically, what it's going to do is, OK, so I'm going to just finish. We're done. So now we can actually say, with stop, we can send through to quit. This Go routine will receive that value. I will finish. Now, the problem with this is that imagine that stopping your server takes a minute. When I call stop, I'm done. The main function finishes, and everything finished, and I didn't free any resource. So actually, when I call stop, I want to wait for the server to say, yes, I'm good. So one way of doing it is actually reusing this in channel. What I'm going to say is I'm going to say stop. And then I'm going to wait on the same channel to receive another Boolean saying, I'm done. So we're going to use the same channel to communicate both ways. So now, this is when this code gets into action. So we're going to say, OK, now we're stopping. I'm going to wait for a second. And then I'm going to be, oh, now I'm actually done. And I'm going to send the signal to the client that is calling to say, now I'm done. You can stop. So if we execute this code, you'll see running task, then server stopping and finishing task and task done. All of that is the server trying to stop. And server stopped is finally when stop is calling. OK, and now this for a gopher, there's a bug. So you cannot answer to this, though. No. OK, so I'm running this code, which is send message. And send message, what it does, I have a list of addresses. And I'm going to broadcast a message, which I say the message and a slice of strings, which is I'm sending this message hi to localhost and then to Google. And what I'm going to do is I'm going to send all of them. And then I'm going to wait for a second, which is a really weird thing to do, but why not? And actually, then I'm going to check if the error was nil. If the error was nil, then return the error, and everything went fine otherwise. So this is not the important code. The important code is the one on top. So what I'm doing is, no, the important code is here. Yeah, the important code is this. So broadcast message, it's here. Broadcast message is the one that giving a message and all the addresses where I want to send the message. What I'm going to do is I'm going to create the channel of errors. I'm going to start all the sending at the same time. So I'm going to try to send the message to all the receivers at the same time. And then I'm going to wait for, so I'm actually expecting as many, I'm going to iterate as many times as addresses they are. So I don't care about anything, so I put underscore. I don't care about the index or the values. I just care about the number of iterations. And if something fails, I'm going to return that error. And otherwise, everything finished correctly. So don't read the part on the bottom. No, wait a second. No, you cannot read that. Whatever. This is too small to read. Anyway, don't read the part on the bottom. But can anyone say what's the problem with this without reading the part on the bottom? They made me write this because the slides are online, so it makes it easy for people not here. But it also makes it easy for people here. So what's the problem? No one? There's a gopher here. OK.
So you have two worker go routines. If the first one sends an error on the error channel, then the coordinator go routine will return and never read the second error from the second worker. So the second worker will block on that channel send.
Yeah. So actually, that go routine will be leaked. So it's the same way we have memory leaks. We can actually have go routine leaks. And we have a go routine leak by so it's, as a consequence, you also have a memory leak. So that was cool, but that was written. So how do you solve it? How do you fix it?
You can buffer the error channel with as many worker go routines as you have. So
Yeah.
you can guarantee that they will never block right to that channel.
That's it. So yeah, you got the gopher. So there's two solutions. One, which is the ugly one, which is saying if I found an error, I will still iterate as many times as I need, and I will just pay attention to all the errors that are coming back. So I will actually read all those errors. The problem is that what if you don't know how many errors might come? Then you might wait forever. So instead, what we do is what you said. We say that this channel, we can write as many values into it without blocking as addresses we have. So now, even if we didn't read any value, all the go routines that are sending values and sending errors into the channel will be able to send that error into the channel, finish, and then they will be garbage collected. Once they are all garbage collected, the channel itself will be garbage collected. if you have a Go routine that is locked, it's actually keeping a reference to that channel. So the channel is not garbage collected, and the Go routine won't be garbage collected either. So this is a tricky thing, so pretty cool. So there's also a different way, which is when you don't know how many addresses there are. In this case, we know, but imagine that you don't know how many values you could actually send into the error channel. What you can do is something similar to what we had before, which is using a quit channel. And now our quit channel is a channel, and what we say is, before we start, we say, okay, we create the channel, the error channel, and the quit channel. And we say, at the end of this function, whatever happens, and I don't care about the way I exit this function, call this, close that channel, the quit channel. And now our workers, they will try to do two things at the same time. One is sending their error into the error channel, but also they will try to read from quit. So now you have eventually hundreds of Go routines trying to send errors into this channel, and you will take care of only one. You will receive the first one, and if that's an error, you're done, and you return. But when you return, quit is closed. And when you close quit, actually, when you're reading from a closed channel, you don't block. When you read from a closed channel, you receive the default value of that type. So all of a sudden, all the Go routines that were waiting here, they will be able to read from quit. They will all get an empty struct, which is empty. It has 0 bytes in it. But it will actually be a signal. So you can actually broadcast to all Go routines using close. It's a pretty cool technique. And all of a sudden, you are sure that with this code, Go routines will never be leaked. Any questions about this code? This is actually the most advanced code that I'm going to show. Probably the last code that I'm going to show, which is good. OK, so yeah, so these are the 12 best practices that I showed. So avoid all the nesting by doing early return. Avoid repetition, so write little types that might help avoid that repetition, like the bin writer that we did. The important code goes first, but before the important code goes the license and documentation. Shorter is better, at least for names. Package with multiple files, it's a good idea to have them rather than have huge files. You should make your code Go gettable, please, and have your functions using interfaces as much as you can, and the smaller interface that you can work with. And 4 last ones. So yeah, break all the dependencies that you have. Avoid concurrency in your APIs. Use Go routines carefully, so both to manage state and try to hide them as much as you can from the usage of your library. So from outside of the library, in our server, that Go routine didn't even exist. We just had start and stop. That's everything. And finally, don't leak Go routines, because leaking Go routines is bad. So yeah, so if you want to learn more, I'm pretty sure that golang.org, you've already seen that before. You also have the tour, which is probably the best way to learn Go. And even if you've written some Go, it's still a very good resource. You end up writing pretty cool stuff. You write at the end a concurrent web crawler. That's pretty cool. And then this is my favorite Go talks, lexical scanning with Go. If you never watched it, is actually Rob Pike presenting how to write a lexical scanner using Go routines, which makes a very beautiful code, and how to, at the end, remove the Go routines and still make it work. And it makes really beautiful code. I think you should watch that. Concurrency is not parallelism, which is more like about the philosophy behind what is concurrency, what is parallelism. They're not the same thing, and if you think they are, you should watch this talk. And then concurrency patterns and advanced concurrency patterns. So if you want to learn more about the things that you can do with Go routines, these are definitely worth it. So yeah, thank you.